So as we've been talking about probability distributions, we've been working with tables, and so naturally we should have the question, can we represent them graphically? And the answer here is, of course. So what I have here is the graph of a probability distribution corresponding to a random variable, which is measuring the number of readings for water control plant, quality control, that violate an EPA standard. EPA being the Environmental Protection Agency. So they are tasked with making sure that our water quality is potable or safe for consumption or whatever use it's zoned for. And so we have here then the number of the measurable outcomes for this random variable. So 0 representing none of the readings violate standards. 5 being on the high end, being that we have 5 readings in this sample or these batches from the treatment pool that are violating an EPA standard. So you should check whenever you're working with these that the sum of the probabilities, so these are the probabilities right here in pink, represented as heights of these bars, you should check that they actually add up to 1, so that this is a valid probability distribution. You can calculate that right now quickly if you are concerned, or if you want to validate that. But the idea then is, what actually are we representing here? And that's what we call the probability mass function. What we were writing as the probability of x, right, which is literally the probability of outcome x, is a function of the outcomes, the measurable outcomes, 0, 1, 2, 3, 4, 5, right? So P of 0, its output is the probability of that outcome, 0.3156. This is specific to discrete probability distributions. So, as we mentioned before, we know that this is a valid probability mass function if the sum over all the outcomes of these probabilities of these probability mass function values is equal to 1. And for each outcome, probability of that outcome needs to be between 0 and 1 inclusive, right? So no negative values, which is why when we represent these graphs, we're always going to have vertical bars that have a positive height. And then we can answer questions like, what's the probability of between 1 and 3 readings that violate? A standard. Inclusive. So 1 and 3 are included in our range of outcomes that we're interested in. So we would represent that as this inequality. X, our random variable, being between 1 and 3, including 1 and 3. So we would have to find the probability of 1 plus the probability of 2 plus the probability of 3, which is the heights of these 3 bars. So that's 0.2622 plus 0.1890 plus 0.1378. And that should amount to, if you pull out your calculator, 0.2622, 0.18890 plus 0.1378. And I got 0.589, which is a valid probability. It's between 0 and 1. And we're saying that roughly 60% of the time, or a little under 60% of the time, we find between 1 and 3 readings violating an EPA standard, which, if you work in quality control, you would know that's pretty high. So the big takeaway then of this should be, what can we learn from probability mass functions and their graphs about the underlying probability distribution? So all of the tools that we learned in the previous unit, where we were examining distributions of sample data, we can start to modify some of them in terms of the language of probability here. For instance, is a probability distribution skewed? Is it increasing or decreasing? Is it approximately bell curve shaped? Where's the center of this distribution? So is it between maybe here, maybe here? How spread out are the data? So we have our range of outcomes from 0 to 5, but what can we consider to be the standard deviation, right? What's an unusual value for this distribution? So would 5 be considered unusual? By what standard? We're going to take all those concepts and in this chapter start to develop them in this context of discrete probability distributions, because they'll be so much more helpful when we get to normal distributions, which carry a little bit more consequence.